All right, chemists, today is the day that we learn a new language. We learn the language of chemistry and chemical compounds, learning how to write the names and formulas for all different compounds, but we're going to start with ionic compounds before going into covalent and then acids next week. For ionic compounds, there's a couple different types of them depending on the ions that are present in the compound. So for specifically today, we're going to start off with type 1 ionic compounds, both binary and polyatomic. Different rules are kind of applied to each of the different ionic compounds as well as covalent acids. So we need to understand what those different terms refer to so that we know when to use each different thing. For the beginning of ionic compounds, we have type 1s and type 2s. The first big important thing is that if we look at all the metal cations on the periodic table of ions sheet that I gave to you, you'll notice that most of the metals in the S block and the P block all have one oxidation state, which is something we talked about back when we did oxidation states before spring break. However, in the D block and the F block, and a couple in the P block, there are a large number of different metal ions that have multiple stable oxidation states. And this is because elements that have electrons in their D and F blocks and they're not completely filled can lose them in a variety of ways due to the attraction of those electrons to the nucleus to form different stable ions depending on the circumstances of the reaction, either what they're being paired with, whether or not it's in an acid or a base, or different temperatures, whether it's really hot or really cold. So different rules apply to the type 1 compounds that have only one oxidation state compared to those of the type 2s, namely because those type 2 ions have a variety of different things that they can be doing. We're going to start, obviously, with the simpler type 1 compounds for the sake of learning the beginning rules. The other part of the different types had a second word on the end, binary and polyatomic. We need to know that binary always refers to two options, like in binary code for a computer, it's zeros and ones. Binary compounds have just two different elements, such as sodium and chlorine in table salt, or manganese and oxygen in MnO there. Those are all binary compounds. Binary compounds are composed of two different monatomic ions in this case. So in sodium, we have the sodium positive 1 ion, we have the chlorine negative 1 ion. Both of those are single ions. Even in the case of MnO2, those are both monatomic. We have a manganese ion and we have oxygen ions. What's different for polyatomics is that polyatomics are a cluster of atoms that are covalently bonded together, and then that whole unit, that whole molecule has a charge because the whole molecule has taken an electron from somewhere else. So for example, CO3 has 1 carbon and 3 oxygens all covalently bonded to each other, and then that group of 4 atoms has gained 2 electrons. Or in the second example, NH4 positive 1, we have 1 nitrogen bonded to 4 hydrogen atoms, and that whole cluster has lost 1 electron, giving it a positive 1 charge. For now, we're going to focus on just the monatomic and binary compounds. To write the names and formulas for ionic compounds, the first rule we need to keep in mind, which is something we've kind of unofficially been doing for a while now, but I wanted to make sure we draw clear attention to it, is that the cation is always named and always written first. The anion goes second. So in the case of putting sodium and chlorine together, it's sodium and then chloride, or Na and then Cl, right? Because the cation always goes first. Second rule comes into how we're actually going to get the formulas for these different compounds, and it's a direct link to what we had done earlier last week when we were using the dot diagrams to find the lattice structures and the formula units for different compounds. That's an important process for figuring out structures and how things link together and shapes and stacking, but it is not important if we just want to find the formula unit. And we can take a little shortcut if we remember that formula units must be electrically neutral. The shortcut involves taking the ionic charges and just making sure that they add up to 0. So from our ion sheet that has all of those oxidation states, if I look up the charge of sodium, we see that it is positive 1. If I look up the charge of the phosphorus ion, also called phosphide, it has a negative 3 charge. Right now, positive 1 and negative 3, they do not make a neutral compound. If I add positive 1 and negative 3 together, I'm going to get negative 2. To make this thing be electrically neutral, I need to have the same total negative charge as I do positive charge. And the only way I'm going to get that in this case is if I have multiple sodium cations. Specifically, I would need 3 of them because if I have 3 positive ones, that adds up to a total of positive 3, and then that would match the negative 3 of my phosphorus ion. So the formula unit for this would be Na3P. A slightly more complicated example would be seen with gallium. Again, if we look up the charge from the periodic table, we have gallium 3 plus, and oxygen has a charge of negative 2. I need to make these two things be electrically neutral, but there's no way that I can make a 3 into a 2 or a 2 into a 3 while maintaining a whole number. So because of that, I need to find the lowest common multiple of each of these. That's going to be 6. So I can get to 6 negative and I can get to 6 positive by having multiple of each of these ions. So to do that, I would need to have 3 oxygen ions. Negative 2, negative 2, negative 2 makes negative 6. And I would need to have 2 gallium ions, because 2 positive 3s makes positive 6. That means that the formula unit when I put these things together is Ga2, because there's 2 galliums, and O3 for my 3 oxygens. And that would be the repeating unit throughout the entirety of the crystal. The more we practice these, hopefully the less you'll be relying on the periodic table of ions sheet. For those of you going into AP Chem, you're definitely going to be expected to memorize the type 1 ionic charges for the S block and the P block. If you go into take college level chemistry, you'll be expected to memorize them there too. And the only way you do that is by practicing more and more of these types of problems. In naming these compounds, we have to identify first what is the cation, what is the anion. We know that the cations are generally going to be metals. So I'm splitting each of these compounds here between the metal, sodium, and the first one, gallium in the second one, and the nonmetal. The cation is just whatever the element is called. It doesn't change in any way. So on the left we have sodium. On the right we have gallium. For the anion, we take the element name, but then we're going to change the ending of it, the suffix. It has to end in IDE. If it does not, you're indicating a neutral atom, not the anion. So those two things imply different things. So if you wrote sodium phosphorus, it's wrong. You're talking about 2 neutral atoms, a metal of sodium and the phosphorus solid. You're not talking about the compound. To make this be the compound, this needs to end in IDE. So this is going to become sodium phosphide. On the example on the right, we have gallium and oxygen coming together to form this compound, but we cannot write gallium and oxygen. That's not a thing. We would need to have gallium, and then we're going to change the ending of oxygen to have IDE. So 2 options would be oxygen, which sounds ridiculous, or we have oxide. And as we know from talking about stuff in the air and stuff we breathe out, this is going to become oxide, like in carbon dioxide. Now, the next 2 slides are entirely practice problems. You should pause here and try to write the name and formula for each of these 3 pairs here. Before you resume, I'm going to go through them. You can skip through my answers to check to see how you did. If you got it wrong, you should obviously go back and fix it. On the next slide, you'll see 2 last ones. Again, I would pause there, try them out on your own, and then come back and check your answers before starting any of the practice work on the practice sheet. For calcium and phosphorus, looking up their ionic charges, calcium is positive 2, fluorine is minus 1. I need to get these to be a common charge, so positive 2, negative 2, and I can do that by having 2 fluorines. This gives me a formula of CaF2, and my name for this, the cation, is unchanged, so calcium. And then we have fluorine, but we have to change the ending to be IDE, so that's going to be calcium fluoride. Example number 2, we have sodium with a positive 1 charge, selenium as a negative 2 charge. To make these equivalent, I would need to have a total of positive 2 to match the negative 2. I get that by doing 2 sodiums. So my formula is Na2Se. The name for this, cation, is unchanged, so sodium. And the second one, selenium, is going to have to end in IDE. That becomes selenide. Example number 3, we have calcium with a 2 plus charge. Sulfur has a 2 minus charge. Positive 2 and negative 2 already neutralize each other, so the formula is just going to be CaS, and the name for that is calcium because the cation is unchanged, and sulfur becomes sulfide. Last two, let's slide it down a little bit. We have magnesium and phosphorus, and then we have aluminum and bromine. To make magnesium and phosphorus be electrically neutral, I need the lowest common multiple again. So I'm going to go to 6 because I have a positive 2 and a negative 3. So to do that, I'm going to need to have 3 magnesium ions to add up to positive 6. I'm going to need 2 phosphide ions to add up to negative 6. So my formula becomes, my name becomes magnesium phosphide. And the formula has 3 magnesiums, 2 phosphides. For aluminum and bromine, I have a positive 3. I can get to a negative 3 by getting 3 of these bromine ions. So the formula unit is going to be AlBr3. And cation name is unchanged, aluminum. Anion ends in IDE, so aluminum bromide. We're going to end there for this video. Next one's going to talk specifically about polyatomics before you get into the practice sheet.